Hi! In this video, we're going to see some examples of the calculation of definite integrals using the fundamental theorem of calculus. And how does that relate to the area under the curve? Alright, this first example is the integral of the quantity x squared dx from the point x equals 1 to x equals 2. Now keep in mind that when we give you a definite integral, an integral that has little numbers representing the bounds, then that's geometrically equivalent to the amount of area underneath the curve, between the curve and the x-axis really, between x equals 1 and x equals 2. So you can see I've graphed the parabola x squared, and I've located x equals 1 and x equals 2, and I can shade that much area between the curve and the x-axis. What's the area of that shape? I can find exactly what the area of that shape is by using the fundamental theorem of calculus. Remember that the FTC stated to us that the integral from a to b of little f dx is equal to capital F of b minus capital F of a. So this is going to be capital F of 2 minus capital F of 1, which I'd be able to get the answer for if only I knew what was capital F of x. Okay? Capital F of x, well actually, because the function in here represents the derivative of the function over here, that means that I can figure out what this function is by just taking the antiderivative of the function in the integrand right there. And we've already practiced that quite a bit for our indefinite integrals. So we're going to actually start this problem by figuring out what the capital F is. The capital F is the antiderivative or indefinite integral of x squared dx. Alright, so if I asked you to integrate x squared dx, what would you say is the answer? X cubed over 3, right, x cubed over 3, and most of you hopefully said x cubed over 3 plus c, where c can be any constant because the derivative of any constant is 0. That's true when we don't have numbers on the bounds. The indefinite integral of x squared is x cubed over 3 plus c. But now, when I add these numbers onto the bounds, you can see that now, geometrically, that represents a very specific thing, the area under this curve. And so for one thing, I'll say I don't need this plus c anymore. You'll see in a minute, it kind of just cancels out. And what I need to do for this is I need to evaluate it at 2, and then subtract away the evaluation at 1. Usually this is denoted with a vertical bar where the lower bound's on the bottom and the upper bound's on the top, just like that. And what this vertical bar says as a symbol is it says evaluate this function at the number 2 and then subtract away the evaluation at the number 1. And that was the right-hand side of the equation that we saw in the fundamental theorem of calculus. Okay, so I'm following through with the fundamental theorem of calculus, where here I'm trying to calculate the f of 2 minus f of 1 part, and that's what this vertical bar says to do. So the only thing I have left to do is put a 2 cubed over 3 right there, and subtract away a 1 cubed over 3 right over there. And that will be 8/3 minus 1/3, and so the answer is 7/3. Okay, so that's actually the answer. You see how I got a specific number for that answer? That's because I had bounds on the integral, making it a definite integral, and it is definitely telling me that the area between the curve and the x-axis from x equals 1 to x equals 2, that area of that shaded region is equal to 7/3 units. Okay? So yeah, that's how you do that. That's how you do the definite integrals, is that you need to find the indefinite integral, and then you evaluate it at the upper bound, and you subtract away the evaluation at the lower bound. Now, if in case you were wondering what happened to that plus c, you could see that if I put a plus c on here, a secret little plus c, any constant, then there would have been a plus c on this part, and then when I subtracted away the other part, there would have been a little plus c on that part as well, and you can see that this c minus that c would cancel out the c's. So that's why we don't need the plus c anymore. It's not really that it's not there, it's just that when we evaluate it here, then it's in its positive form, and then we subtract away the evaluation here, so it gets subtracted off, and so the plus c doesn't really matter. Okay, so we can just get rid of that right there. And keep in mind that when you're doing integrals that have bounds, when you're doing definite integrals, you don't need to include the plus c because it would have canceled out anyway when you subtracted the values of the antiderivative. Alright, so now let's try another one. Here's one for you to try. The integral from 1 to 2 of the function 1 minus x dx. And here I've drawn a picture. Here's a function. Its y-intercept is 1. Its x-intercept is 1. And now, this is a little bit different than the last problem. I'm asking you to calculate the area from x equals 1 to x equals 2. And it looks like this area, a triangle actually, is below the x-axis. I wonder what's going to happen here. What value are we going to get for the integral? Now I want you to pause the video and try to calculate this on your own. And remember, your first step is going to be to find the antiderivative for this. And then you evaluate that antiderivative on both the bounds and calculate the difference. Go ahead and try it out. Okay, so let's see what you did there. First of all, what is the antiderivative of 1 minus x? Okay, well, the antiderivative of 1 is x. And then minus x goes to minus x squared over 2. I think, is that really the antiderivative? Well, just like in previous lessons, you can check your work at this point, and you can say, well, the derivative of x is 1, the derivative of minus x squared over 2 is x, and so you can check your work thinking about differentiation to go backwards and confirm that you got the correct antiderivative. And you'll want to do that before you do the next step, because the next step is you're going to need to evaluate that at 2 and then subtract away the evaluation at 1. Okay, so let's see what value we got there. We got 2 minus 2 squared over 2. Alright, now that's the evaluation f, capital F, at the number 2. And then we're going to subtract away the evaluation at the number 1 right there, so that's minus capital F of 1. And let's see what we get out of all of this. That's 2 minus 2, so that's 0, minus 1 minus a half, so we got a half inside there. That's kind of weird. For this answer, to represent the area under a curve, I actually got the value minus a half. Now you might think that's a little weird to get a negative value for an area, but it actually is true, because inside calculus, when the area is underneath the x-axis, when it's below the x-axis, then that signed area has a negative sign. When the area is located above the x-axis, then that area has a positive sign. It all goes back to those little rectangles that I was defining in the FTC video. Remember, the width of the rectangle was dx, and the height of the rectangle was the function value. So when the function is above the x-axis like this, that results in a positive number. When the function is below the x-axis like this, it actually results in a negative number. So sure enough, mathematically speaking, the area of this rectangle is minus 1/2, and that's because the rectangle is located below the x-axis. When we calculate these areas using the fundamental theorem of calculus, every time the graph dips below the x-axis, that area counts as a negative amount. Okay? Alright, let's try a couple more examples here, and we'll just stick to the computation of some definite integrals. You can draw a picture on your calculator or by hand if you like to see the picture, the corresponding picture. Okay, so let's try this integral from 0 to 1 of x squared times 1 cubed times x times dx. Remember that now that you have bounds on that integral, I am going to be looking for an actual numerical value in your answer to that question. Another example we have, the integral from 1 to 3 of 6 divided by x squared dx. Okay, so these are some exercises for you to try right now. So please pause the video and see how far you can get on both of these before you watch the solution. Are you doing it? I hope so. And I hope that you remember the steps. The first step in calculating a definite integral is actually figuring out what the indefinite integral is. Once we've got the indefinite integral, we just evaluate it at both of the bounds and we take the difference between that. Now these are a little more challenging. Actually, this is probably the more challenging one if you actually did it out, right? How did you calculate this integral? Did you times this out 3 times and then times it by x and use power rules? No, use u substitution, right. So for an integral like this, just to figure out the indefinite integral, I need to do a u substitution where u is equal to x squared plus 1, and then du is equal to 2x dx, 2x dx. I only have 1 x dx right here, and so I have to divide by 2 to say du is equal to x dx. That's because I have x dx right here, so I want to match it with an x dx right there. And so now that, in indefinite format, is equal to the integral of u cubed times du over 2. Okay, so notice that when I'm going through this u substitution, I am not putting the bounds x equals 0 and x equals 1. I am not copying those over to this integral right here. That's actually very important because when you do a u substitution, you're really translating the problem into a whole nother space of variables. You're talking about the question now and what we've been referring to as the u space. Now, x equals 0 here, but it doesn't mean that u equals 0 over here. In fact, when x equals 0, u is equal to 0 squared plus 1. So if I wanted to put bounds on it, I would put a 1 there. And when x is equal to 1 up here, u is equal to 1 squared plus 1, which is 2. So if I wanted to put bounds on this u integral, I would have to put a 2 up there. Is that a little confusing? Yeah, I thought that might confuse some people, so that's why I say don't even put the bounds. Just don't put the bounds, continue with the u substitution, and get back into the x space, and then we will use the x bounds. Okay, so to continue with this problem, I'm going to try to figure this out in the u space by taking the 1/2 to the outside and saying u cubed du. Then I'm going to integrate it into u to the 4th over 4, really plus c, but I know that the plus c's will cancel out, so I'm not going to write plus c. I'm just going to write u to the 4 over 8, and now going back into the x space, that's actually the quantity x squared plus 1 to the 4 divided by 8. Okay, remember that the first step in calculating definite integrals is finding the indefinite integral. And so everything you see on the board so far is just me trying to figure out what is the indefinite integral, and I finally found it. The indefinite integral is this quantity. Remember, before you move on to the evaluation of the bounds part, you're going to want to take a minute to pause, take the derivative of this function, and make sure that the derivative of this function matches the integrand in the integral in question. Now I'm going to leave that to you to do on your own. Don't forget to use the chain rule and multiply by the derivative of the inside function when you're checking your work there. Okay? Now once you've confirmed that you do in fact have the correct indefinite integral, this is where the vertical bar comes in, and we're going to say that we're going to evaluate this on the original bound from x equals 0 to x equals 1. Okay, so that means that we're going to do 1 squared plus 1 to the 4th over 8, and then we're going to subtract away 0 squared plus 1 to the 4th over 8. Okay, and this is actually 2 to the 4th over 8, so 16 over 8 here. And then this is 1 over 8 right there, and so 16 minus 1 is 15, and so we get 15 over 8. So the final value of this integral is 15 over 8, and that's the amount of area that's underneath the curve. Go ahead and graph it, and you'll see that corresponds to a certain amount of area between the curve in question. This is what you would be graphing if you want to see that, between x equals 0 and x equals 1. Okay, now let's try it again. Why don't you go ahead and try this one out? Did you remember how to take this derivative here? Before you even start, I would suggest moving the 6 to the outside just like this, and also rewriting the x squared on bottom as x to the minus 2 on top. Alright, now you can see that I did carry the values of the definite integral. I carried the bounds over here, and it's okay to do that because I didn't change it to a u space. It's not okay to do that when you change into a u space, but if you're just rearranging the integrand, that's totally fine. Okay? on to the next step where the 6 is just going to carry through, and I'm going to integrate this function into minus x, or actually you may see it this way, minus 2 plus 1 is minus 1, and then I have to divide by the minus 1 like that. Did I do that right? Did I find the antiderivative correctly? Well, I just like to take the derivative of this function in my head, and sure enough, it matches with the x squared right there. So yes, I did that correctly. And so now I'll go on to the part where I have to evaluate it at 3 and subtract the evaluation at 1. Okay, what to do with the 6? Now, some people will want to put the 6 inside there. Some people will want to leave the 6 on the outside. It doesn't really matter as long as you're consistent. I'll keep the 6 on the outside, and then I'll say this is really minus 3 to the minus 1, and then minus another minus of 1 to the minus 1. Oh man, that's a lot of minus signs. So make sure you don't get confused with all those minus signs there. I guess alternatively, you could have even brought this minus 1 to the outside and just had a minus 6 on the outside. Alright, so let's see what that is. 6, and then we have minus 1/3, and it looks like those minuses will turn into a plus, and we're going to have plus 1, and so we're going to have 6 times 2/3, and so all in all, we get 12 over 3. Final answer, 4. We got exactly 4 as the area under the curve 6 over x squared from the point where x equals 1 to the point where x equals 3. Alright, now one final thing I want to show you is not really an example, but it's a general rule when you're integrating functions. Let's say that you're asked to calculate a definite integral, let's say maybe the integral of the square root of 4 plus x squared from 2 to 2 dx. Now, first of all, I want to say that I don't really like this integral. This integral looks really hard to do. I don't know what the antiderivative is because 4 plus x squared is under there, and I don't see any 2x or any x on the outside to help me with my u sub. I'm going to say that this integral is actually very hard to calculate. But the saving grace is that they're asking me to integrate it from 2 to 2. 2 to 2, that means you didn't go anywhere, right? So really, if you wanted to see what a picture of this curve looks like, it actually looks like this. And sorry, if there's a minus sign, it looks like that. And here's the point where x equals 2 right here. And they're asking me to figure out what is the area under the curve from here to there. I didn't go anywhere, and so I didn't accumulate any area, so the answer is 0. And that's not just special because when you plug in 2, you get 0 right there. Actually, if I asked you to integrate from 1 to 1, right here, here's x equals 1, what if I integrate from 1 to 1? You see, I didn't really go anywhere, and so once again, the integral would be 0. Actually, that's a general rule, and the general rule is that when you integrate from a to a, and you don't go anywhere, it doesn't matter what function you're trying to integrate, f of x dx could even be unknown to you, the answer there is always 0. Okay, so if you see a definite integral where the number on the bottom bound is the same as the number on the top bound, you don't even have to find the antiderivative. You just answer 0 right away because you have not accumulated anything because you weren't told to go any further than you're already at.